The second part of chapter 6. Right now, really encourage you to be focusing on the chapter 6 homework. Come see me during office hours on Zoom. Please note again, it takes some time to grade quiz 3, exam 2. And this is a quick turnaround. There's another quiz coming up April 20th. If you're considering dropping, let me know. We can talk about that if you want. We're having another lecture on a bonding theory, though this bonding theory is very different than the others that we've looked at. So I'm going to try and point out the distinct differences. I will also continue to bring up what those old bonding theories, the benefits, the limitations, things like that. Main focus we'll get into is diagrams, and it's going to look quite complicated, but really we're going to focus on just the period 2. These diagrams can get far more complicated, so we're doing some introductory diagrams. We'll see how that can help us calculate bond order. That can also help with magnetism. No bonding theory so far has addressed magnetism. And then we'll again talk about how the diagrams can get a little more complex at the very end. So we're finishing up chapter 6, and then next week you can see chapter 7 and quiz 4. Okay, so right off, you're going to see this is the molecular orbital theory, or the MO theory. And this theory goes back to what we know about electrons. Electrons are in orbitals, okay? They're not like Lewis. They're not just dots that we know exactly where they're at. They're in a region, a probability, okay? So we spend a lot of time on that with electrons. But now if they're bonding, we're going to talk about how these orbitals combine. Okay, so we're combining something that's very confusing. An orbital has these very unique shapes, and then we combine them and form molecular orbitals. Okay, so the idea that we're going to be talking about is that we start with our atomic orbitals, and then we're creating molecular orbitals from those. Okay, and this rule is going to look familiar. The number of molecular orbitals is going to equal the number of atomic orbitals. That sounds really familiar, possibly to hybrid orbitals. The number of hybrid orbitals equal the number of atomic orbitals. But this is definitely a different theory. And I'll probably say this many times. It's this terminology of localized versus delocalized. Okay, so in valence bond theory, we talked about the orbitals being specific on each atom. Those were localized. What we're talking about now are delocalized orbitals, therefore the whole molecule. Okay, so that's why this is the molecular orbital theory. So let's revisit some of the orbital discussions we've had before about electrons, and that's electrons are waves. They're also particles, so we want to revisit. If we add waves, we have constructive interference. If we subtract waves, we have destructive. So there's the add constructive and then subtracting destructive. So this is the same thing, except now we're doing it for molecules. Okay, so this I think is not too difficult to see. We got one s orbital, one s orbital. If we merge those together, now we can see that that's one bonding orbital. Okay, so that is now a bonding orbital, and we're going to call this delocalized. It's over the whole molecule, and the notation is sigma 1s. It's the bonding of the 1s orbital. So we're looking specifically at hydrogen right now. So then it gets a little strange because now we're subtracting. Okay. Adding is constructive interference, subtracting is destructive interference, and you can go back to our slides on orbitals ages ago and see that they can be out of phase. So this blue and red is indicating that it's out of phase, so it's anti-bonding. That's the asterisk here, and you can see that this is higher in energy. Okay, I didn't point that out last time. You see this is lower in energy, and this is higher in energy. So that's called bonding, anti-bonding. We put them together, and you can see we have an orbital down here, lower in energy, that creates bonding or stability. and we have a higher orbital up here that is destructive or destabilizing of a bond. So that's the constructive, destructive interference. So what we're doing is creating an understanding of these orbitals, bonding, anti-bonding, and then we make a diagram. So you can see here, the diagram we just created is in the middle. And it can look as simple as bond, bond. So that's bonding, anti-bonding. So I'll just even label it that way. Bonding, anti-bonding. And what's on the outside are the atomic orbitals. So hydrogen has a 1s, and if it's bonding with another hydrogen, that's in the 1s. So you can see those electrons are going to bond like we've seen before. It's going to go into the orbitals with lower energy first. They're going to spin pair, and now that's going to form a bond. There's nothing up here in the anti-bonding. So that's the MO diagram for hydrogen. Okay, so very simple. One electron each. We added at the bottom. Now we've got 2 electrons. That's a bond. Okay, we can add to this. The next one is helium. Okay, so helium has 2 electrons, and if it's a diatomic helium, then it's another helium, 2 more electrons. So we fill the bottom first, spin pair, 1 up, 1 down, and the bonding is full now. So if the bonding is full, we have to move up in energy to the anti-bonding, and we calculate or we add electron here and electron there. So this is showing that we have 2 electrons in bonding, 2 electrons in anti-bonding, and that's going to be how we set up these diagrams, and then we're going to use those to interpret. This is not stable. Okay, as you can imagine, if the instability is even to the stability, then that calculates and it cancels out. Okay, and we'll do a calculation for that here shortly with the bonding order. So what about this example? He2 plus. So that plus means that we lost 1 electron. It could be from the left or the right, it doesn't matter. We've got 2 electrons over here, 1 electron here, so that fills the bonding orbital first. And then now we only have 1 left over to go to the anti-bonding. Okay, so then we're going to calculate the bonding order, and that's going to be the bonding electrons minus the anti-bonding electrons divided by 2. So here we've got 2 minus 1 divided by 2. This has a bonding order of 1/2. So this does exist. 1/2. It does have somewhat of a bond. I know right now that's strange. It has a half bond. That's weird. But remember when we were doing resonance in the chapter before, and we talked about it's not a single bond, it's not a double bond, it's in between. This bonding theory gives us a better understanding of that. So this is a bonding order of 1/2. If we go back up here, we can see our bonding order is 2 bonding electrons minus 2 anti-bonding electrons divided by 2. That's why it is not stable, because it does not have a bonding order. So if it's 0, it is not stable. If we go back to the hydrogen, you can see that's 2 minus 0 divided by 2. That's a bonding order of 1, and just like Lewis showed us, our bonding order should be 1. There should be a single bond between the hydrogen molecules. So this is how the diagram helps us to get to bonding order. So now let's move it up. Let's go to the P's. Okay, so P, you can see here the blue overlapping is in phase. So this figure is actually a typo. You can take a look at your textbook. This is just a typo here. This should be bonding and anti-bonding, but the figure was a mistake in the book. But you can see the bonding is when the blue overlaps. the anti-bonding is the blue-red. So that's out of phase. Then you can see if it's out of phase, it's not going to be a bond, it's anti-bonding. So that's our problem there. So that's just one p orbital, that's the px. So the pz, you can see now, if it's in phase, blue matches up with red, that's our bonding, and that's the 2p pi bonding. I wouldn't be worried too much with the names. I just want you to see the pi, the sigma. This was the sigma because it's between the atoms. And the pi is above and below. Okay, so here's out of phase, anti-bonding. In phase, bonding. You know, again, outside of the nucleus, and anti-bonding. So we just did 6 molecular orbitals, and now you can see definitely the diagram gets a little more complicated. Okay, so what we did is we took the 3p's and we said there's a sigma bond, bonding and anti-bonding, and then there were those 2 pi's here and here. So this is the diagram setup. This is the diagram setup that we did for 1s hydrogen. It looks the same. This is just now 2s, boron, carbon, nitrogen. You see it has 2s here, but it's one lower, one higher. Okay. Pay attention here though, this is a little annoying and can be frustrating. This is for boron, carbon, nitrogen. Okay, so the first 3 in the P block, and you can see the boxes. There's one box here, 2, 1, 2, 1. That's the pattern for the diatomics boron, carbon, nitrogen. We change this ever so slightly. Look at this for oxygen, fluorine, neon. The last 3 in the P block, this stays the same. 1, 1, and now we have a switch here. That's 1, 2, 2, 1. Okay, so 1 box orbital diagram, 1 box, 2, 2. The top's the same. What changes is right here, these 2. Okay, it goes from 2, 1 to 1, 2, and then of course these are the same. So you need to know these diagrams, and you'll be able to then, depending on what you're given, the substance, then you can fill out the diagrams and interpret what that means. One thing I just wanted to note, what we just showed, we had that 1, 1, 2, 1, which switches to 1, 1, 1, 2. The reason is this terminology is called mixing. Okay, so just like when we had in atomic orbitals, when we saw there were exceptions to 4s and 3d, like the energy levels would change, that's what's happening here. The energy levels for boron, carbon, nitrogen look very similar in this order, but when we get farther along, the energy levels have rearranged slightly. Okay, so that's why we have this different pattern here in the diagrams. So let's take a look at what this gives us. Okay, boron, carbon, nitrogen, they have the same pattern, 1, 1, 2, 1, 2, 1, and we take in the electrons and fill them up. These are the diatomics, and take a look what it tells us. Nitrogen, we saw this in Lewis, that has a bond order of 3. That's a triple bond between the nitrogen atoms. Okay, take a look at oxygen. That's a bond order of 2. Okay, please note here, take a look at this difference. 1, 2, 2, 1, different patterns. And what do you notice here about oxygen? Oxygen's got unpaired electrons. That's where we started this chapter. That's the first bonding theory that's been able to describe why liquid oxygen is magnetic, because of these bonding orbitals, these molecular orbitals that we've now got the diagram for. They show the pattern of the bonding, and we have unpaired electrons here. So you can see the key then is have the diagram, use the electrons, fill up the diagram, then you can calculate bonding order. That's this column here. You can also determine magnetism looking for unpaired or paired electrons. So we have paramagnetic, diamagnetic, paramagnetic, and diamagnetic. So that's what we're looking at using these diagrams. And mentioned in the beginning of this chapter, liquid oxygen is magnetic. This doesn't help us. This doesn't help us. It's the molecular orbital theory that can say why this is the case. Oxygen is magnetic. So let's do a couple. Draw a molecular orbital diagram for C2+. So you have to take into account how many valence electrons carbon has, lose one electron, and then of course think about the diagram. So go ahead and pause this if you want to do this, and draw the diagram and fill it out. Take a look here. Remember the bottom 1-1 pattern is the same for all of them. Carbon has that pattern where it starts with 2 on the bottom and then 1. Okay, so if we do that, and if we've got 7 valence electrons, so there were 2 down here, 2 down here that fill up, okay, and then again, whether you do it 2 on the left or 2 on the right doesn't matter, but it fills down here. And now you can do some calculations. Okay, so that was 7 electrons. I've got those drawn in. The bonding electrons. So remember, the lower in energy. So this is bonding, and this is bonding. This is an anti-bonding. So it's 5 bonding minus 2, and we can get these fractions. Okay, so that's bonding order of 1.5. That does exist. Because we have one unpaired electron here, it is paramagnetic. So this is how we use these diagrams to answer these questions: bonding order and magnetism. Okay, another example is N2-. So the diagram that we just saw, the 2-1 diagram for carbon is the same for nitrogen. We add an electron because it's N2-. So now we just have to distinguish between this is bonding, this is anti-bonding, these are bonding, this is anti-bonding. So if we put those in, then we can come up with 2, 4, 6, 8. So that's these 6 and these 2. And the anti-bonding are these 3, and that gives us a bond order of 2.5. And again, because we have an unpaired electron, that's paramagnetic. So the diagrams we introduced were homonuclear. Those are the same atoms, diatomics, and we just added a negative, made a positive. We're just adding or taking away electrons. These are examples of heteronuclear. So your textbook has some of these. So you can see HF is different. So this is the atomic orbital of hydrogen. This is the atomic orbitals of fluorine. Those look different. That can then throw off why the symmetry and how things look for the molecular orbitals. So I just wanted you to be aware these exist. When I'm on campus, I usually tell students, come see my upper division textbooks, have molecular orbital diagrams for really, really complicated examples, and it's overwhelming, but it's interesting to see how the theory can apply. You could Google that if you want, MO diagrams, and you could see even more complicated versions, but just wanted you to see these exist. But what you're going to be responsible for is the 1s versions, that was the hydrogen examples, and then the 2s and the 2p, both diagrams. So we have this diagram and this diagram. So that's what you'll be responsible for quizzes and exams. And that concludes chapter 6.